All right, let's look at a couple more. Let's find this page that has the two triangles that are similar. So for A and B, recognizing that those side lengths, AC and DF, are equivalent, and AB and DE are equal, and that angle in between them is the same. The ratios are equal to each other with 1, which means they are in fact similar, yes. If so, use your flowchart. I'm not sure what a flowchart is, but that's fine. So when it says, are the triangles congruent? You have your work in part A that helps support the answer in B. It's true that two pairs of sides are equal, but that's not enough to prove triangles congruent. But you have, see how you have the S, the A, and the S up here? I'm wondering if you have learned the side angle side congruence theorem for triangles. So if you have two sides and an angle in between them, that's the same, then the two triangles are congruent to each other. So just the two sides, you're partway there, but we need that angle in between. So try to kind of maybe rewrite that and include that SAS part. And that helps support the fact that they're congruent, not just similar. For the problem, I think this one was right below it, where you have the two angles that form that straight line. They add up to 180, so you did 180 minus 52 and got 128. 3x plus 1, if that equals 128, divide that, or subtract that and then divide by 3. Just make sure that you're showing, let's see, maybe like this part right here, that it equals 127. And it looks like, I don't know, are you putting divided by 3 right there maybe? So just something like that. And that would support that answer over there. So yeah, that looks great. That looks, let's see, and it doesn't say anything about rounding, so I would say keep it in that form. Awesome. All right, this problem here, I had to actually look up the rule for rotating again. I used to love teaching translations and rotations. It was kind of a fun lesson or a section to teach in geometry just because it's super like hands-on as far as getting those rotations to happen. For a counterclockwise rotation 90 degrees, you take an original XY value. I'm wondering if you know this definition or not. You switch X and Y and you make Y, the Y coordinate, negative in that X location. So that's what would rotate that entire shape 90 degrees in a counterclockwise direction. So if A is 3, 2, then A prime, you'd reverse the order. So you'd go 2, 3, and then you'd make the Y coordinate that's now in the X location, but you'd make it negative. B prime, same idea. If B is 4, 9, B prime would be 9, 4, and then make the 9 negative. C prime, same thing. 6, 7 becomes 7, 6, and then that value is negative right there. So if you plot those points, we'd have negative 2, 3. There's where your new A value would go. B is all the way over to negative 9, 4, way over here. And C is at negative 7, up 6, like so. Connect from A to B to C. And you can see you're rotating from one quadrant to another. That's 90 degrees. Counterclockwise means you're kind of going backwards around a clock. So you'd be going in that left direction. So negative 2, 3, negative 9, 4, and negative 7, 6. That would actually be the response for A. Hopefully that makes sense. All right, let's try this problem. So it says, examine the relationships that exist in the diagram below. We have parallel lines being cut by two different transversals, and you're supposed to find the lengths in any order, or the lengths, the measures for angles A, B, C, and D. C and D are both correct. Very good. Which I know I put a check mark. I'm kind of the opposite of how normal teachers grade things. I put a check if it's right, and then I cross it off if it's wrong. So hopefully that doesn't throw you off when I put a check by something. That actually means it's correct. So yay. All right, from there though, if we look at the two parallel lines, you know D is 68, so is C right there. On the opposite side though, there's a connection with A and that 97. And that's kind of similar to one of the problems I had you fix on that last video. If they're on the same side of that transversal line, those are called corresponding angles. And we used to actually have, when I taught geometry, it was a postulate, not a theorem. But those two angles should be the same. They should both be 97. So A would equal 97 degrees. If A is 97, we could use some information about this triangle and the fact that D is a vertical angle with 68, or D is a vertical angle with the angle inside the triangle, so they would both equal 68. So if that angle on the bottom right corner is 68 and A is 97, to get B, just do 180 minus the other two angles, 97 and 68, and that'll be your B value. I can't remember if this is a new page or not. So it says examine the triangles below. For each one, solve for X, name the tool you used. I think for that first picture, it's a right angle. We know another acute angle, and we know two of the side lengths. And I think you've used this definition before in one of the earlier worksheet pages. We can use either sine, cosine, or tangent. If 58 is our acute angle, 6 is the length of the opposite side, and X is the adjacent side. If you write then tan of your angle, which is 58, equals opposite, which is 6, over adjacent, which is X, we'll just do that cross multiply again, but this time when we cross multiply, the X goes with the tangent, so the X isn't already by itself like it was before. I'm wondering if that's maybe what threw you off, not sure. And then 1 times 6 on the right is 6. So in order to solve for X, we do need to isolate it. Moving tangent over, since it's being multiplied with X, we're going to divide by tangent. And then you'll do the same thing on the other side. So then you'd use your calculator and just do 6 divided by tangent 58. And that would be the length of the adjacent side. All right, that next example in the middle with the 7 and the X. This is an example of one of the special right triangle rules. So I hope that sounds familiar to you. This dash here and here mean that they're the same length. So this is not coming out on my pen. Let's try that again. This is isosceles. So really, it helps us label that right side, but it doesn't really give us the X value. If it's isosceles, we also know that these two angles would have to be the same. They're called base angles in an isosceles triangle. If you have a 90-degree angle at the top and those two angles have to be the same, they would each have to equal 45. So this is an example of not only an isosceles triangle, but a 45, 45, 90 triangle. And that's a special triangle rule. That could be the quote-unquote tool you use, I suppose, to describe what happens with the hypotenuse. The hypotenuse is always bigger than the two sides by a value of radical 2. If you take the side length 7, whoops, sometimes I think faster than I write. It happens all the time. If you take the side length of 7 and multiply by the square root 2, that product would show you how much bigger the hypotenuse is from the two sides of that isosceles right triangle. But then the last one, this is the one I'd asked your mom about. Have you seen law of sines and law of cosines before? If you have, then you are in a super advanced geometry class. That is surprising to me. I don't teach that to my kids until trigonometry, which is a couple years ahead. But it is what it is. Looking at this picture, since there isn't a right angle, we can't use sine, cosine, or tangent, but we know the sides and then the angle in between. So if you know a side, an angle, and another side, that's SAS, you can use law of cosines to solve. So that would be your tool. Let's see if this looks familiar. There's a couple of ways to write it out. When I write it out like x squared equals the two side lengths squared, so 15 squared plus 18 squared. Almost looks like Pythagorean theorem, but then we subtract out a really big product here. And that product is going to be 2 times those two sides times cosine of the angle in between. So cosine 32 degrees. Does that look familiar? If it does, that would be the way to solve for x. Now, when you type it into your calculator, you got to kind of be careful. So do 15 squared plus 18 squared minus that whole product. So if you can, try to type it all in at once and get just one answer without doing it in little parts and trying to add and subtract those parts together. Then you'll have x squared equals some big number. To get x by itself, you'd square root each side. And that would give you the length for that side right there. If you haven't learned that formula yet, if that just looks super strange, well, it looks strange anyway, let's be honest. But if you haven't learned it yet, I guess I'm not totally sure what your teacher's looking for as far as a different means to solve. That would be the only thing I could think of. So hopefully that does look familiar, and you can plug it in and find the value for x.